Thanks, Bob, and good afternoon to everybody. I'm going to talk about a case study of maritime that has many applications in thinking to many other domains as well, and I hope you'll be able to sort of make those leaps of imagination as I go through. First of all, I just want to give a couple of slides which explain the context of the maritime case study and the complex sea spaces that surround particularly the UK. In terms of the growth of different uses of the sea space, particularly noticeable in the North Sea. And the picture on the left-hand side here shows the situation from a few years ago, where we already had a number of wind farm areas, they're the green splodges, and quite a few oil and gas installations, which tend to be the smaller black splodges, and the interaction of shipping tracks, which you can see shown here in pink. Mainly hugging the coast and going into the major ports such as Felixstowe and over into the continent, into Rotterdam and the like. So quite an interesting mix of uses of the space in which shipping is attempting to safely and efficiently navigate and keep the flow of trade while allowing all these other uses as well. We also have a context of ships getting larger. So I'm showing here the Algeciras, which is the largest ship to call in the UK in June last year. It carries 24,000 20-foot equivalent unit containers. It's 400 meters or so long and 61 meters wide. So these things are enormous. And you're probably aware of the situation in the Suez Canal, where a ship a little bit smaller than this, 20,000 TEU, has currently got completely stuck. And there's the possibility that they may have to unload 20,000 containers to refloat it. So these things are monsters and can get into difficulties. Part of that competing marine space, I've shown you here the turbines. That is something which is increasing rapidly, as I'll show you in the next slide, how that is becoming more and more of a challenge to these competing uses. We also expect to see increases in ship size over the next decade, and potentially more ships. Certainly a sort of 30% increase in trade is expected by 2030. We also have the emergence gradually over that period of autonomous vessels. The technology for that is actually getting quite advanced. The regulatory processes for autonomous vessels are rather behind. So it's a little bit uncertain when we'll actually see autonomous vessels in our sort of space. But all of these things tend to mean that we're looking for a greater management of the sea traffic overall. I've got here two pictures which try to show, this is the Irish Sea, show the situation of what's happening with the growth of wind farms. So just a couple of weeks ago, the Crown Estate, who owned the seabed, announced the winners of concessions for renting out the seabed for wind farms. So the red areas here on the left are existing wind farms off the coast of the Irish Sea, off Liverpool particularly. And the yellow areas are the new concessions of what's called the Round 4, and would be expected to be in place and operational probably by 2025, 2026. And on the right, you can see overlaid on that the shipping tracks of 28 days of shipping. I can't remember which month this is, but you can see that there's a significant number of ships and traffic that go through the new wind farm areas. So you've got to imagine that those ships will be displaced and largely have to sail around those new areas and between gaps in them. And therefore it's becoming really quite congested, even in the Irish Sea, let alone the North Sea. And therefore the need for resilient positioning, navigation, timing information in this sort of complexity is ever growing. In fact, we've got to look at the whole of the economic exclusive zones for the UK and potentially for Ireland, from our own interest in the GLA, looking after UK and Ireland. That's an extensive sea space, as you can see shown there. And we want to bring resilient P&T throughout that space for all types of users, not just ships, but ideally also for other marine uses as well. They are huge economically significant areas. And the significant thing about being an island is that we're a long way in general from other land masses. Obviously, we have Europe out to the east. To the west, we don't have very much, just the odd rock in the middle of the Atlantic, but really not very much at all. So it's quite a challenge when thinking about where to put terrestrial transmitters for terrestrial systems. There are limitations in the actual landmass space of where these things can be placed. And something that actually makes it obvious that satellite systems have a certain inherent advantage. We also have quite a challenging space in terms of the signal reception. Paul has just explained what receivers are having to do, which is a very complex situation. Even when they can receive signals directly and are not interfered, but of course they can be interfered. We can also have obscuration of signals, so things can get in the way, particularly when you're on ships which are near to port infrastructure, or even be obscured by the ship's own superstructure. And they can get reflections, and again, reflections are multipath of those signals. Can be from nearby objects, or again from the ship's superstructure itself. So in fact, we have what becomes quite a complex multipath environment on ships, which many measurements have been taken in various projects and trials. And we see that the threat of that is that you can have several simultaneous faults on multiple satellite signals, all happening at the same time. And the conventional methods of detecting these sort of faults have difficulty when too many of those signals are affected. A single faulty signal is a little bit easier to detect. When you start to multiply that up by 2 to 3, even 4, it starts to get really quite challenging to detect what's happening. Okay, so as Washington pointed out, we need to start with some very clear requirements and very carefully specified. Now we have in the maritime domain the International Maritime Organization setting out a set of requirements and the need for resilient positioning, but in terms of the conventional parameters of availability, continuity, integrity, and accuracy. So they're all defined relative to a geospatial reference as the chart. So the chart datum is fundamental to understanding the reference system that the ships are using. The accuracy is broken down by the different phases of the voyage. So we tend to look particularly interestingly at the coastal phase, the 10-meter accuracy phase, 10 meters, 95%, which is quite a challenge in itself. And in some ways, it's not that well defined because coastal can mean lots of different things. As you've seen from the complexity of the sea space, on some coasts there would be relative less complexity. On others, it can be an incredibly congested environment. So having just one number that goes for all of that is a little bit questionable into the future. On an oceanic basis, we're looking at a much slacker requirement of 100 meters. So the accuracy is quite challenging, but the real challenge, I think, in maritime often comes with the balance between integrity and continuity. So the integrity risk is less demanding than some applications, such as aviation. Here we're looking at a 10 to the minus 5 integrity risk level, compared with aviation at around 10 to the minus 7. And we're looking at a time to alarm of about 10 seconds as opposed to 6 seconds. So it looks like we've got a bit of an easier job, but we do have quite a strict continuity requirement, and every false integrity alarm is a break in continuity. And that's why there is a delicate balance between those parameters, which not everyone really appreciates. And it is quite difficult finding solutions that will meet both integrity and continuity. And as I've just talked about, the multipath environment on ships is particularly challenging, and therefore ensuring that we spot faulty signals within the receiver that have been affected by multipath or noise or interference is actually more challenging than it is on an aircraft, where you tend to be over the 200 foot decision height. You're well away from the ground. There's not quite so much superstructure as there is on a ship, and the antenna would tend to be quite well and quite well placed and actually be regulated into where it's placed. On a ship, it could be virtually anywhere. Everything's fighting to get to the top of the mast to get the greatest look at. So these are actually, in the end, quite challenging requirements, and I think still need to be looked at from a total level of safety point of view, in the way that aviation sets out its safety case. So that's something that we're still looking into, and hope to take back our thoughts to IMO in due course. And then here I've captured the idea of having, in terms of fallback systems, to having primary, alternative, this is UK, primary, alternate, continuous and emergency type PNT provision. This has been looked at recently within the UK PNT strategy to try and understand in each sector, including maritime, what systems we have available and how they're categorised in this way. In maritime, through the International Association of Lighthouse Authorities, we tend to have something which is similar to this, but not quite the same. We look at redundant systems, backup systems, and contingent systems, where redundant systems would have an equivalent performance to the basic GNSS capability, which these requirement numbers are really based on. We look at the backup of potential systems, which would allow a ship to get to a safe refuge, and therefore would need to be reasonably performance capable over the medium term. That may be 2 to 3 hours. This is sort of the hours in which we're looking at the integrity risk. Or we can look at a contingency system, which will allow a much more short-term completion of a safety manoeuvre, such as a collision avoidance situation, or avoiding even getting into a collision avoidance. That would be much shorter term, maybe of the order of a few minutes, maybe 15, 30 minutes as a maximum. So the idea that the PNT systems could be put together in some way that provide these different levels of capability, of redundancy, backup, and contingency. We then have to look at the sort of systems that can be brought in to complement GNSS. And we're looking at systems then which are dissimilar from each other and from GNSS, and in particular have independence from GNSS, so that when GNSS vulnerabilities occur, then these systems are not affected. They inevitably have vulnerabilities of their own. All radio navigation systems can ultimately be jammed, but a number of these, notably ELARAN, is quite high power and is far more difficult to jam than GNSS. So this is a little table, an extract from a table of a study that was done by University College London for us, to look at the various capabilities of sort of systems that could be brought into play in a potential system of systems. And the yeses are obviously good things here against various requirements, and the no's are where they're not met. And you can see there's quite a lot of no's. So getting systems that are anything like as capable as GNSS is really quite difficult. And in order to construct something which can have reasonable capability, you really need to look at a mix of these systems and put them together in various ways. Okay. So taking it forward from there, we used the ESA funding in a project called MARINAV, Maritime Resilience and Integrity of Navigation, which had the intention of looking at a system of systems solution for maritime PNT to build both resilience and integrity into our critical national infrastructure as part of our aids to navigation services for ships at sea and in ports. And some of the results I show here are taken from the MARINAV project, not all, but those interested, all the reports from that project are available online. And if you have time to dig into into at least the top level reports, I think they're fairly approachable because I wrote them and they're not too technical. Okay, so we started to look at how we could put together this system mix into a system of systems. And the way that we prioritized that and looked at the mix was to look at the the geographic coverage area of the systems. So the system with the greatest coverage area, because it isn't geographically constrained, is dead reckoning on ships. Dead reckoning, which can be either inertial dead reckoning through an inertial measurement unit, or it can be the conventional dead reckoning that ships are fitted with a velocity log and a gyro compass, and therefore can dead reckon the position from those inputs. But they're available on board the ship and are not affected by things like jamming. They tend, though, to have a very high drift rate. So they're very good under dynamics in the very short term of maybe a minute or two, but not so good over longer periods. In fact, the sort of holdover capability that will provide is, for an affordable dead reckoning inertial system, is probably of the order of 2 minutes at most. But then we looked at that to GNSS with its global coverage. In fact, the integration of DR and GNSS is a very well-established technique in many fields, through to different ways of coupling them together and providing some resilience to jamming in doing that. So that's a very well-worn route of combining DR and GNSS. And then we looked to add ELA-RAN, which in the days when we had transmitters in Europe, and I'll talk about this in a few minutes, gave us quite a large coverage, and still potential for a UK system could give quite a significant coverage. We then go to a more regional system, which is a ranging mode of VHF data exchange system. So the VDES system is the modernized AIS. It contains the AIS capability at its heart, but it's a much wider VHF band, and it allows 32 times the data transfer capability in that wider bandwidth. But in particular, adding then a timing signal to the VDES signals can produce pseudo-range measurements rather like GNSS. So this is another terrestrial system to add potential to ELA-RAN and throw into the mix, albeit at a more regional scale, which I'll explain in a moment. And then perhaps at an even lesser regional scale is the use of ship's radar to look for coastal matching of features, or to see how the image of the radar varies over time, and to use that to apply into a dead reckoning type technique. So within this, we're assuming that the GNSS is multi-constellation with GPS and Galileo, at least, and potentially the other constellations, well, Beidou and GLONASS, which some ships are equipped with, all of which are recognized internationally as being allowed within the SOLAS regulations. Putting that together with space-based augmentation, EGNOS in Europe, and into the future, looking beyond current EGNOS v2 into version 3, and complementing that with receiver autonomous integrity monitoring in the ship's receiver. So these are key to providing integrity on ships, and being able to spot when satellites are transmitting the wrong signals is very much what SBAS can do, whereas determining the local effects of multipath on ships and disturbances to that information is what the RAIM system can provide. And if we look into the future, and these are question marks, we do see a potential benefit to a low Earth orbit PNT system. We looked for a number of years at the STL system, satellite tracking and location, which was based on the Iridium constellation. Frankly, that is not coming good and doesn't look like it's really a solution. Of course, in between this and the UK Space BNPT, there's the possibility of using OneWeb. But I don't think anybody who understood PNT ever thought that OneWeb was ever going to become a PNT system. So I don't even mention that here. And we now in the UK are looking at some form of space-based PNT system, which could be a LEO system, but isn't actually specified yet. Requests for information have gone through to industry, and that's been looked at quite carefully. And certainly there is a place within this mix of systems, within our overall GNSS, for something like that. I've mentioned that DR can be supported by radar processing. But the thing that I need to just add on to here is a proprietary system called the Carta that is in use at some ports around the world and provides a very localized pseudo-light type system for ports, and it does appear to be quite effective. So the ship needs all of these systems coming together. So you can see the global, the regional, and the local systems being picked up by the ship's transmissions and receivers. It's supported by a range of communications functions and through e-navigation services which harmonize data onto the ship. And then there are the onboard systems such as the dead reckoning. And very importantly, there's the mariner in the heart of this, trying to understand how all this information is put together. But that's our overall system of systems coming together actually on the vessel. Outside of that, here, this diagram at the heart of it, the big box, has got the multi-system receiver and navigation processing that goes on in the ship. But that's surrounded by the space infrastructure and the terrestrial infrastructure that's required to provide all of those signals, including the communications. So I've got the cloud on the right-hand side, which is a depiction of the maritime connectivity platform, which itself is a system of systems for communications, which includes the VHF data exchange system at its heart. So we've got within this several systems coming together as a whole system of systems. So it's really quite a complex architecture when drawn out in full. So here's the depiction that is taken from the UCL study of how the different terrestrial and space-based information can be brought together on the ship through a way of providing integrated navigation. So down the left-hand side is the basic route to the GNSS when working properly and not being interfered with and not being degraded, provides the PVT information. But running alongside that continuously is the system that looks at dead reckoning, pulling in together the IMU or the velocity log type information, and then feeding that in with the GNSS information into a multi-system integration algorithm and providing PVT from that route as well as a combination of the space and terrestrial and onboard systems. Just a word about ELARAN, which is still at the heart of our system of systems as having the longest reach and the greatest overall capability. Low frequency, 100 kilohertz. It uses precision UTC locked timing and all-in-view receivers. So in many ways, it's a terrestrial sort of equivalent to GNSS. Three transmitters are needed to give 2D position and time. Though a single transmitter will distribute precise time. And just a note to say, this is nothing like the original LARAN C. It's like comparing black and white television of the 1950s to your multimedia that you've got in the lounge now. So ELARAN has potentially a part to play within time dissemination for the UK, based on the MPL's National Timing Centre that's currently being put together to duplicate and give resilience to UTC clock information for the UK. The National Time Centre will also distribute time, particularly through dark fibre, to key locations, which is a very good method at very precise, but also quite relatively expensive. So there are other methods which include two-way satellite time and frequency transfer, or two-way low-frequency time transfer that can be looked at. We're particularly interested in getting very precise time to shore-based transmitters in remote locations, sort of places that will never achieve the dark fibre connections. And maybe ELARAN has a place in getting time to those sort of locations. But equally, it's land locations, the sort of transmitters you might have on land. And 5G comes to mind in that respect. So here's the coverage picture of timing from the Anthorn transmitter up in Cumbria. So this is as it could be now if it were properly upgraded, which wouldn't take a lot to do, but it does need to be tied to UTC from the National Timing Centre, something that still needs to be done. On the left-hand side, you can see the timing coverage. The dark blue is the very dark blue is getting under the 10 nanosecond coverage at the very bottom, through the 50 nanoseconds and above. So coverage in the left is for an uncorrected, no differential correction system with an internal antenna, inside a building, which is something that GPS really finds quite a struggle to provide timing indoors. But it's actually quite an interesting capability. And if you go out of doors and you add differential corrections, then you get 50 nanosecond timing or better throughout the UK and the EEZ. So as recently as 2014, 2016, we had very good coverage of ELRAN with the NELS system through the international transmitters in Europe. That ceased in 2016 when France and Norway turned off their transmitters, saying Galileo offers resilience. Interesting statement. But in the European Radio Navigation Plan by 2018, we see statements of Galileo as vulnerabilities. So there is a changing attitude in Europe, and one wonders where they might go next. So our proposed system would use existing infrastructure rather than building new ELRAN masts, and live guy wires effectively, looking for interoperability at TV masts. So this is a novel technique, but could potentially give quite a good capability from TV masts at the corners of the UK. That gives a geometry which will give a 20-metre coverage quite widely across the UK. In the right-hand picture, you can see the light green contour, which is the 20-metre coverage area. If we could bring in even one transmitter on Europe, it would make a large difference. You can see the green contour here expands considerably. If we could just get SILT in Germany, and you can see that over on the extreme right in the picture. That's the transmitter which still, all the infrastructure is there. It's mothballed but being maintained. So there is just a possibility that that could come on the air at some point in the future. When looking at these sort of coverage plots, often asked, well, what would happen if we increase the transmitter power? Could we get more coverage? And I think an important lesson here is, here we've got our corner transmitters in the UK on the left-hand side with a 1 kilowatt, providing a reasonable sort of coverage, but not ideally what we want. Even upping that to 10 kilowatts, and you can see the picture is virtually unchanged. So beyond a certain power level where it's sufficient so that you can receive it and decode that in the receiver, increasing the power is not the answer. Whereas by contrast, as we had a moment ago, if we bring in the SILT, which changes the geometry of the transmitters very significantly, then you're much better off. The lesson here is that it's geometry of the transmitters that matters more than anything else. And here's a really interesting plot that I don't think anyone will have seen before, because this is newly produced. This is the effect on the right-hand side of the coverage that you can get if you had a very accurate clock on a ship. And it's quite interesting that coverage really expands very significantly. So we're very interested in the advent of quantum technology clocks, which hopefully could be installed on vessels relatively cheaply and allow the sort of capabilities that we see here, which is even better than the original system we had with ELRAN in 2016. To that, we want to add the VHF data exchange system with R mode. That's VHF upgrading the AIS with passive pseudo-ranging results based on existing AIS stations being upgraded. Here you need 3 measurements to provide unambiguous 2D position fixes. And this is at a moderate TRL. A lot of work has gone on in Germany and in the Baltic, where there is more opportunity for good geometry of these types of transmitters. We have something of a problem, though, in the UK. So on the left-hand side here, we can see, the green is the 20-metre contours of capability, given all those existing VDIS stations or upgraded IS stations that are on the previous slide. And you can see that there are large areas of the coast, very importantly down the North Sea, where we have very little capability. And again, this is down to geometry. We simply just cannot get the geometric position of transmitters to get the coverage. Very important area for us is the channel. So here's the channel, and what we're showing here with the addition of 2 or 3 VDIS R-mode transmitters in France, we start to get coverage of a very important, very busy part of the sea lanes around the UK. So some international cooperation with France would certainly help this element of the system of systems quite significantly. Ship's radar is at a lower TRL, but looking at ship's radar to provide positioning information has some interesting methods of being complementary to DR, a sort of SLAM technique, processing the radar imagery. It's still really at a proof of concept stage. We're keen to do more trials, which COVID have recently prevented, unfortunately. And we'd like to explore the extent to which passive reflectors or even active E-raycons, radar beacons around the coast as further aids to navigation could help this. But the picture, the yellow shows where we would have more information from ship's radar, and the blue, again down the North Sea with the flatter, less featured coastline, shows that we probably get rather poor results from this sort of technique. And the clue is really to couple all of these things together. So this is a picture of coverage in the channel. If we could couple R-mode and UK-based ELARAN. So we've not got SILT in this. It's purely a UK-based ELARAN system, but we do have the French R-mode transmitters. And now we start to push out the 20-metre contour quite significantly towards the edge of our EEZ. So this is now looking like a really quite capable system. And then finally, my last, I'm overrunning on time, but finally I wanted to do a word for the user. Everything that we do, and this has come up in certainly everything that Washington said, is puts the user at the beginning, the center and the end of our PNT solutions. We need clear use cases and the user requirements that go with those use cases. And the user needs then will govern the direction for solutions. And when you look into the user need, you often get statements like, we need greater accuracy, we need less than a meter. But actually what they mean when you question that further is we need better integrity. We need to be able to trust what we're using. And we need to carefully consider the human factors. We know that they contribute to a very large percentage of accidents. We need to worry about the way we portray information on displays, and that should be appropriate to the data quality. The user applications, the way that they use the data, should have an understanding of that quality, especially by looking at the statistical variation of the data and taking account of that in the way that it's used. So resilient PNT is fundamental for the situational awareness of users, for the mariner here in particular, fundamental to providing them with the right decision support tools. And the resilient PNT and the human factors together are key in future autonomous operations, where people will still interface with those vessels, even if they're on the shore. So what we need to do throughout all that I've talked about, lots of technology, but what we need to make sure that we do is to put the user at the center of those solutions. And thank you.